Hello, everyone. In this lecture, we want to talk about modular arithmetic as one of the first preliminary technology that we need to understand growth 16. Okay, so modular arithmetic is a system of computation over integers in which a number resets when they reach to a specific value that we call modulus. Uh, for instance, when we want to compute 27 mod 26, it is like drawing a circle start from 0 until to 25. And then to compute a mod of 27, we need to start to turn around this circle. You start from 0 and then count and turn around this circle to reach to the target value. So here the target value is 27, and we want to circle around the turn around this circle. So we start from here, 0, and count 0, and then 1, 2, 3, 4, 5, 6, and then continue this counting to reach here 23, 24, 25, 26, and 27, right? So here we have reached to 27. And now we see that this 27 is kind of equivalent to number 1 on the circle. So then we say that 27 mod 26 equals to 1. Or we say 27 is equivalent to 1 mod 26. Okay. For negative value, we do the same thing, but we turn on the left direction. So let's clean these lines. Okay. And then you want to see for the negative value. You want to compute minus 3. Okay. So we start from 0 and then we count. 0, minus 1, minus 2, and minus 3. So here, this is minus 3. And so we say that minus 3 mod 26 equals to 23, right? Or minus 3 is equivalent to 23 mod 26. So, so other than turning around the circle, we can do this mod in other methods. For instance, to compute 27 mod 26, you just compute 27 minus 26. And this would be equals to 1, right? Or to compute minus 3 mod 26, you compute 20 mod 3 plus 26, which is equals to 23. And another method is to dividing the value over the modulus. Like for instance, we want to compute 228 mod 101. So to compute 228 mod 101, we can do the same thing, turning around the circle, or we can compute 228 minus 101, and again minus 101, or we can divide 228 by 101, and then the remainder would be the correct answer. So then this is different method that we can compute the mod values. Or 142 mod 101 equals to 41, and then again a negative value, minus 5 mod 101 equals to minus 5 plus 101. Okay, so in our website, we have a tool that allows you to compute mod values. Okay, so let's check the website now. Okay, want to click on the website. And so this is our website. So here on the section ZKP and then subsection growth 16, you can find mod arithmetic. So you can compute the mod value. For instance, I want to compute 170 and then the value of mod maybe 101. So then the result is 69 or maybe 905.54 and then the result equals to 45. Okay, so then you can use from this tool in our website to compute the mod values. Okay, so let's go back to our discussion. After modular arithmetic, we want to compute and discuss modular addition. So for instance, suppose that we have two values A and B, and then we want to add these two values in the modular arithmetic. So we have two methods. The first method, which is the left side of this equality here, says that you can first add these two values A and B to each other and then compute mod P. And the second method, which is the right side, says that you can compute A mod P first and then compute B mod P and then add these two to each other and finally again compute mod P. So let's see if this equality is correct with an example. So we want to compute addition of 181 plus 127 mod 101. So you will see multiple times about 101 as the modulus because the growth 16 that we have designed and the example is working over this value. So we want to work with the values that they are used even in the growth 16 system. Okay, so we want to follow the right side. So first you compute the first value mod P. So 181 mod 101 equals to 80. So you can check this by using our website. And then 127 equals to 26. And then we finish this step. Now we want to add these two values to each other, which is 106, and then finally compute mod 101, which is 5. So this computed by following the right side. So now the left method. So the left method says that you can add the two values first to each other. So let's add these two values to each other. So this is equal 308. And then compute mod P, which is mod 101 equals to 5. Again, you can check in our website. Okay, so let's check this in our website to see if it's correct or not. Okay, 308 mod 308 mod 101, which is 5, right? So that was correct. Okay. After modular addition, we want to discuss polynomial addition in modular arithmetic computation. Okay, so suppose that we have two polynomial f of x and g of x. So based on our previous knowledge, when we want to compute addition of these two polynomials, we just find the same degrees of x and then add these coefficient to each other. So this means that the coefficient of x to the power of 3 in f of x and the coefficient of x to the power of 3 in g of x, they should be added to each other. The same thing for the coefficient of the x to the power of 2, x to the power of 1, and x to the power of 0. So based on our discussion on the left side, let's say that you can add these two values to each other first. Okay, if we add these two values to each other, the sum equals to 125. Then by adding these two values to each other, we will reach 70. Adding these two values would be 111. And adding these two values to each other, 123. So then now again, we compute mod of the coefficient of the polynomial by 101. So 125 mod 101 equals to 24, and then mod 70 mod 101 equals to 70. The same thing for 111, and then for 123. Okay. So now we want to discuss modular multiplication. So it says that if you have two values like A and B, and you want to compute them in modular arithmetic, you have two methods. The left method says that you can multiply the two values to each other first, and then compute mod C. But the right formula says that first compute mod A, and then compute mod B, and then multiply the two values to each other, and finally compute mod of the final multiplication. So let's follow this multiplication formulas with an example again. We want to multiply 121 by 147 and then compute mod 101. So the right side formula says that first compute mod of the A value. So 121 mod 101, using the website, you will see that it is equal 20. And then 147 mod 101 equals to 46. And then multiplication of these two values is 920. And using the website, you will see that 920 mod 101 equals to 11. Okay. So let's follow the left side formula. So the left one says that first multiply the two values to each other. Okay, so by multiplying these two values to each other, we will reach to this big number. And then if you use the website, you will see that mod of this value equals to 11. So both formula is correct to computing the multiplication of two values in modular arithmetic. Okay, so now we want to discuss polynomial multiplication under modular arithmetic. So suppose that we have two polynomial. Again, using our previous knowledge, we know that to compute multiplication of these two polynomials, we need to multiply each of the elements of f of x in both elements of g of x. And then the next element also should be multiplied by both elements of the g of x. So by multiplying these two polynomials to each other, we will reach to this polynomial with degree of 2. And then now we want to compute the coefficients values in modular arithmetic. So we need to compute 791 in mod 101, and it would be equal 84. You can again check the website. And 1582 mod 101 would be 1999. So no, these two values first, they are added to each other, and then the result would be compute mod 101, which is 99. And then 266 mod 101 equals to 64. Okay. Okay. Now we want to compute modular division. So the formula says that if you want to compute A divided by B mod C, first you need to compute the inverse of B, and then your division would be converted into a multiplication. So for multiplication, you first uh, uh, can multiply these two values to each other and then compute mod, or you can compute A mod C and then compute the inverse of B mod C and then multiply two terms to each other and finally again compute mod. But the challenge here is that how we can compute the inverse of a value in modular arithmetic. Okay, so let's follow with an example. 2700 over 34 mod 101 equals to 2700 multiplied by the inverse of 34. So the question here is that what is the inverse of 34? So it should not be a float value because as you remember, we mentioned that in modular arithmetic, all values should be between a range of 0 and p minus 1 when p is the modulus. So this means that when we are working on mod 101, so p here equals to 101. So all values should be between the range of 0, 1, 2, and until 100, right? Remember that circle that start from 0 here, then 1, and then 2, and then reach into 100 in our example. So then we cannot say that the inverse of 34 is a float value. The inverse should be a value from this circle. So how we can compute and find a value in this circle that's equals to inverse of 34? Okay, let's see. So we say that in modular arithmetic, the inverse is a value that's when you multiply the a number with its inverse, their multiplication should be equals to 1 in mod p, which is 101 here, right? So this means that if you want to compute inverse of 34, you need to multiply 34 with a value, and then the multiplication equals a number that if you compute mod 101, you will reach the value of 1. And this is the question, how we can compute this value. For instance, suppose that we say x equals to 5, right? So 34 multiplied by 5 equals to 170. And 170 mod 101 equals to 69, right? So their multiplication equals to 170 and mod 101 equals to 69. But we are reaching a value that's the final result equals to 1, not 69, right? So then we say that the inverse of 34, it is not 5. So let's discuss an algorithm that you can follow to find this inverse value. Okay, so to discuss this algorithm, we need to review the Fermat-Leader theorem. The Fermat-Leader theorem says that in modular arithmetic, when you pick your p-value, which is 101 here in our computation, so any value from the range to the power of p minus 1 equals to 1. And based on this theorem, we can divide the two sides of this equality by x. So then we will have x to the power of minus 1 on the right side, and x to the power of p minus 2 on the left side. So, and this formula says that, okay, if you are seeking x to the power of minus 1, you should compute x to the power of p minus 2. So for our example, if you want to compute the inverse of 34 to the power of minus 1, the inverse of 34, we need to compute 34 to the power of p, which is 101 minus 2. And then this means that you need to compute 34 to the power of 44. So if you compute 34 to the power of 44, it is equals to the inverse of 34, the value that are seeking to compute this division here. So now how we can compute 34 to the power of 99? So one method is that you compute 34 by itself and then compute mod, again, multiply the final result by 34 again and compute mod, and repeat this process 99 times, right? Or 98 times. But a simpler protocol here says that if you want to compute 34 to the power of 99, you can convert 99 into the binary form, which is 113011. And then using this binary form, you can convert the 99 into the different powers of number 2. So here this is 2 to the power of 0, 2 to the power of 1, to the power of 2, 3, 4, and 2 to the power of 5, and then 2 to the power of 6. So then you can convert 39 to the power of 99. So you will have 1 here, so it would be 34, and then you have 1 here, so it should be to the power of 2. So here it should be to the power of 2 to the power of 5, which is 32, and then here 64. And then you need to compute each of these terms, each of these 4 terms, which the final one is just 34, and multiply to each other, and then compute mod 101. So how we can, so this algorithm, the whole of discussion after this is just to compute this big value, right? 34 to the power of 99, how we can compute easier compared to multiplying 34, 99 times to each other and then compute mod, right? So this algorithm is easier. So now we have 34, and 34 to the power of 2 equals to 1156. And using the website, you will see that mod 101 equals to 45. So computing 34 to the power of 5 equals to computing 34 to the power of 2, and then again to the power of 2. And we have 34 to the power of 2 from previous step, which is 45. And 45 to the power of 2 is 2025. Mod 101 equals to 5. So 34 to the power of 8 equals to 34 to the power of 4 and then to the power of 2, and 34 to the power of 4 from previous step equals to 5. So then 5 to the power of 2 equals to 25, mod 101 equals to 25, and 34 to the power of 16 equals to 34 to the power of 8, and then to the power of 2, which is this part from the previous step equals to 25, 25 to the power of 2 mod 101 equals to 19. So next step, 34 to the power of 32 equals to the 34 to the power of 16 to the power of 2. From previous step, it is equals to 19 to the power of 2 equals to 58. And finally, 34 to the power of 64 equals to 34 to the power of 32, and then to the power of 2. From the previous section, it is equals to 58, and then to the power of 2, and mod 101 equals to 31. So now we computed 34 to the power of 60 here, and then 34 to the power of 32 here, and then 34 to the power of 2 here, right? Now we need to multiply these values to each other, and then we will have the big values, and after computing mod on the website, you will see the final result is 3, right? So the final result is 3. So this means that 34 multiplied by 3 should be equals to 102, and mod 101 equals to 1, right? 102 mod 101 equals to 1, because you can compute 102 minus 101, which is 1. Or you can turn the circle, or you can use the website. Okay, so we have reached this value. So we were seeking a value that when we multiply by 34, and then the results wrap around in the mod 101, the final result equals to 1. So this means that the inverse of 34 equals to 3. Okay, so let's go back to our division. It was 2700 multiplied by inverse of 34, which is 3. And then if you multiply these two values to each other and then compute mod 101, the final value equals to 20, right? And 20 again is a value in the circle that start from 1 and then reach to the 100, right? Because when we are working in mod 101, all values should be inside this set from 0, 1, 2 until 100, right? All of computation that you will do, the final result would be a member from this set. So this is the member from this set. In previous lecture also, we saw that the final result was a member from that set, right? So here, so you see that this is also a member from that set. All of this quotient value also, they are inside that set. Okay, so so now we want to use a tool in our website to compute the inverse value easier than following this protocol. So we have this tool in our website because in next lecture, you need to compute the inverse of values. So we don't want to follow this time-consuming protocol. So let's see how in the website we can use this, we can compute the inverse. Okay, again, in the section ZKP and growth 16 and modular arithmetic, you have a modular inverse here, okay? So you can enter the mod value here. Let's put 101, which was our uh, in, modulars. And then let's see for the 34 if the value, the inverse equals to 3 or not. Okay, so yeah, so the value equals to 3. The inverse of 34 equals to 3. The inverse of 3 also is 34 because 3 multiplied by 34 or 34 multiplied by 3 equals to 102, mod 101 equals to 1. So let's compute 45 inverse. It is 9. 63 inverse equals to 93. If you multiply 63 by 93 and then using this mod calculator, you will see that the final result mod 101 equals to 1. Okay, so now we introduce our website. For the next lecture, also, we will again use this our website to make the computation easier to understand. Okay, thank you so much. And we will discuss the next topic in next lecture. Thank you.